Okay, let's start. Again, good afternoon, everybody. Today, we have a pleasure to receive here at Unidade Acadêmica de Física, Dr. Prosper Nyassor from INPE. Dr. Prosper is going to give us a seminar. Let me start with a brief presentation of our speaker. Dr. Prosper is graduated in applied physics at University for Development Studies in Ghana. He has a master's degree in physics here at UFCG. Dr. Prosper was a student of us in the past, and he has a PhD in space physics at INPE. And now he works at INPE in the capacity building program. And he's engaged in equatorial aeronomy research and with focus on gravity waves studies, and is on this subject that he's going to present his seminar today, that is entitled Source of Concentric Gravity Waves Generated by a Moving Mesoscale Convective System in São Martinho da Serra. I think the presentation is going to be in English, but at the end, I think Dr. Prosper can also answer questions in Portuguese. Prosper, thank you for accept our invite, and it's a pleasure to have you here in our department.
Thank you very much for the opportunity also to share with you my research work so far. I'm really grateful. Okay, so can I start now?
Yes, yes.
Okay. Good afternoon to you all. I think I don't need to talk much because Dr. Fabio has already introduced me. So this afternoon, I'm going to give a brief talk on sources of concentric gravity wave generated by a moving mesoscale convective system in São Martinho da Serra. My presentation will take briefly this format. And then, this work actually is a collaborative work between people from São Martinho da Serra, some from INPE, São José, and others from Campina Grande as well. Okay, a brief introduction. Okay, first of all, I'd like to talk briefly on what atmospheric gravity waves are. Okay, gravity waves in general, they are waves that are generated as a result of interaction between two forces. The first force is the buoyancy force, which acts upward on the air parcel, which is an equilibrium state, and then it displaces this air parcel upward. And then in an attempt for this displacement to be restored, we have gravity, which acts downwards to restore this displacement caused by the buoyancy. But then on the first trial, normally it's not able to get it directly to the equilibrium state, but rather it goes beyond downward the equilibrium state, as we can see in point 3 here, before finally getting up to equilibrium state. So as we can see, we have a cycle of oscillation here, which is as a result of the interaction between the buoyancy and then gravity. And then any other oscillation that occurs after this first cycle is what we call gravity waves. So this is the basic generation mechanism of gravity wave. And I would like to also mention that at this particular point, the buoyancy here usually deposits its momentum and energy when displacing the air parcel from the equilibrium state. So the wave we are seeing is actually one way or the other, the transport of energy and the momentum deposit here. Since the atmosphere is always trying to attain equilibrium, so these waves needs to propagate, thereby carrying this energy and momentum deposited during the upward movement until this energy and momentum finally disappears. So in summary, this is how gravity waves are generated. Now let's go straight to the point here. We are talking today about concentric gravity wave. It's actually a gravity wave which has a similar mechanism of generation as I explained previously. But then in this case, I'll focus only on convection. Convection, in other way, let me say, is just clouds. Okay, the clouds we see every day in the sky. So what happens is that we have a layer in the atmosphere known to be the tropopause, which is quite a thick layer. And then when you have clouds being formed, they get to this layer where they cannot go further upward. So they spread below this particular layer. And then with time, when the clouds build up, they have this kind of warm air that is always moving upward inside the cloud. And this is due to the buoyancy I showed earlier. So when this movement, upward movement, which is technically known as the updraft, kicks the tropopause very, very high, when it kicks very high, it displaces the tropopause upward. So this upward displacement is just like what I showed earlier on, where buoyancy pushes the air parcel upward. Then gravity set in trying to restore it back to equilibrium, but it could not restore at the first try, so it pushes it down into the cloud. Then finally, it comes up again. Then from there, we have this type of gravity, which look circular in nature. And then as it propagates higher and higher, the circle becomes bigger and bigger and bigger and bigger until it's observed in whatever medium that is used to observe these waves. And in our case, or let's say our research group both in INPE here and then in Campina Grande Physics department, we use air glow, which I'll talk a little bit about it in the next slides. So we observe these waves, as we can see up here, having this bright and then the dark structures. So this is the concentric nature of the gravity waves we are talking about, which in summary is the concentric gravity waves I'm talking about. And then I'd also like to mention that we do have other sources of concentric gravity wave, but I'll just restrict myself to convective system in this particular talk. Okay, so if anybody is interested to know more about this, you can refer to our paper in 2001, which gives a detailed description of what I just explained here and then other cases. All right, gravity waves in general, well, let me be specific, concentric gravity wave, they have some properties, And then the property is one, where they exist. And as I said earlier, they propagate. So at which frequency are they propagating, which is a characteristic of gravity wave, because we have other types of wave, and the properties is what we use to differentiate between them. Then we also talk about the propagation. In this case, we're talking about it propagating horizontally or vertically. And then we talk about the observation. So the first question for me to answer here is, where do they exist? And I would like to say they exist in a stratified atmosphere. So when we talk about stratified atmosphere, we are basically talking about an atmosphere that varies with density or varies with temperature, which is the basic principle of formation of buoyancy. So it has to have this property for it to support the generation first and also to support the propagation. So it exists in stratified atmosphere. And then the propagation propagates at a period of few minutes to several few hours. And then its propagation, actually, we have it propagating both horizontally and then vertically, as I showed. As you see the concentric structure expanding, becoming bigger, it's actually moving also vertically upward. And then for the observation, the question here is, how do we observe gravity waves? So to observe gravity waves, what happens is, as the wave propagates through the atmosphere, there are certain atmospheric phenomenon that this wave leave their traces inside. So we use these traces to observe them, such as air glow, and then we have temperature as well. We can use the air glow and temperature, but for our group, we are dealing with the air glow, which I will also talk about later. Okay, so some few observations. The first observation I would like to talk about is overshooting. I showed it briefly. Sorry, let me just go back. What you see here, okay, this upward pushing that you could see here, or this bump structure you see here, is what we call the overshooting. So how do we observe this overshooting, and how do we know we have an overshooting? So in this study, we use satellite observation to know that, and this is an example. Actually, this image was taken on the International Space Station. The details is given here. And then for us to know an overshooting in the visible range, it appears this way. So now you can see that you have some kind of pushing, or let me say boiling region within this particular arrow, where the arrow is pointing. And this is what we call overshooting. But then we have another way of also knowing that we have an overshooting, that is using infrared image. Okay, I've not shown it here, but for the infrared image, wherever you see any structure of this kind in infrared image, it appears to be the coldest region on top of the cloud. So that is what we use to know that, okay, now it has actually overshot upward, because we know the tropopause to be the coldest region between the troposphere and then the stratosphere. So anytime we see anything colder on top of the tropopause, we know that that is an overshooting. Okay, now let's talk a little bit about some concentric gravity waves activities that have been observed specifically in Brazil. So far, we have reported one work so far in literature that has been shown, or let me say, I've presented some cases of concentric gravity wave events. And these events were also observed in Martinho da Serra. And today's talk is also going to be in Martinho da Serra, because we actually found out that what I'm going to talk about is quite different from the traditional way we used to do things. So we have to come out with a different kind of methodology in order to investigate the sources, which will not follow this one. So for this particular work, which is currently a published work, we observed it 3 cases, 1 in 2017, and then 2 in 2018. And then when we talk about concentric, we are not only talking about a circular gravity wave, we also talk about arc-like. As you can see here, we can only see an arc here, which is also a type of concentric gravity wave. And then this one, we could see some dark structures here, which look circular. And then we have dark and bright structures, which is also another type. And then we have the third one, which also look arc-like. So what we did here was that we have observed these waves, and then we want to know the properties of this wave. We use spectral analysis, which again, I'll talk about, because this one is more or less like a literature review. So I'll talk about these methodologies in the methodology section, which will follow soon. So after we know the properties of this wave, that is the horizontal wavelength, the period at which it's propagating, and then the speed of this wave, we use a numerical method in order to follow through, that is to follow the wave propagation, either back in time okay, to the source, or forward in time to where the wave is going to give off all its energy, or let me say to dissipate. And then this numerical technique actually helps us to do it step by step in each time till we determine the source. That is, if we come back in time, this numerical method will give us the source of this particular wave. And that is exactly what we did here. This numerical method is known as the retracing mode, where you feed in the wave parameters, and then with the background atmosphere, that is the wind and temperature, we are able to now see how the wave propagated in the atmosphere until where it was generated. So the upper panel here is the time versus the altitude propagation of the wave, and then the lower panel is showing the latitude and longitude propagation of the wave. Then from this result, which I'll not go in details because I'll talk more details in the next slide, we found out that this wave we see here, actually for this wave, we traced the first concentric structures seen in the image for all of them. And then the dashed red circles we see here is actually the first wavefront of the concentric gravity wave we observed in the OH emission layer. Then starting the ray tracing from this particular, one of the location, because this one is concentric, so you can pick any location at all. Then we start from one of the location here, then we trace it from the altitude of 87 kilometers, which is the OH emission layer, back in time down to the troposphere to see where exactly this wave was generated. And in all the cases presented here, the ray tracing showed that this wave was most likely generated in a very region where we have the cloud top to be very cold, which is an indication that we have an overshooting. And that is exactly what we did here. But having the ray tracing pointing to this place is not enough for us to conclude. So we went to another stage where we decided to estimate, okay, by how much this updraft is able to push the tropopause into the stratosphere. By how much? Because according to literature, if you have this overshooting by 1 to 3 kilometers, you have a higher chance of concentric gravity generation. So we decided to investigate this to see that, okay, if in this region we have the cold regions, which signifies overshooting, this overshooting are they more than 1 kilometer for us to say, okay, it's more than 1 kilometer, for that matter, it has a higher chance of generating this wave that we observe. And indeed, for the 3 cases we observed first, we realized that all the overshooting, averagely, the overshooting for all the cold top, that's the cold cloud top temperatures, we realized that they are more than 1 kilometer. So in that case, we are sure that we have an overshooting which has satisfied this criteria. Therefore, this system, or one of these systems, are most likely to be the one that generated the wave we saw. Then the next thing we did was that, okay, if in terms of height, we are able to show that we have an overshooting more than 1 kilometer, then what about the distribution of this overshooting point, which I can also call the convective cores, okay? The very cold regions are normally known as convective cores. So we want to see if these cores here, okay, are close to where the ray tracing is pointing to. Now, I would like to explain here the blue asterisk and then the blue full circle here is actually where we have the tropopause position of the model wind. And then the red one is where we have zero wind. Okay, the model wind means we use the wind in the ray tracing to follow the propagation of the wave. Then the zero wind means we didn't use the wind, we only ran it without the wind. Okay, so where these things stop, that is the model wind stop, we compared it to the place where we have the position of the cloud top. And then here we realize that considering the error margin of our estimation, we realize that, okay, where the wave tracing is stopping, which shows that that is where this wave was generated. It's not so far from where we have these cold regions, which is an indication that this system here are most likely to be the one that generated our waves. And then for the second one, we could actually see a very good correspondence between this blue one, that is for the stopping position and the purpose position of the retracing, and then the convective course, the distribution of the convective course, and also the center of the circle. They are very close, which are within the acceptable range. And then for this one also, even though they are quite far, further analysis showed that this overshooting course here were actually the one that generated the wave that we observed. So basically, this is the first case we have actually presented from Brazil in literature. Other ones are currently under development. So methodology. As I said, we are dealing with air glow. Okay, so specifically for gravity studies, we are using the OH air glow, which is around 87 kilometers. And the instrument used to do this observation is known as the all-sky imager. Now, the all-sky imager in its operational mode, okay, takes image of this form. This is the original image taken by an all-sky imager. And then this white dot that we are seeing here are actually the stars. And then the light we are seeing at the northern parts of the image, and then the southern parts is actually an effect of city lights close to the observation site. And then we could see some white trend, or let me say gray trend here. This is the Milky Way. Okay, so we have all these things captured by the all-sky imager. But then in this particular state, it is very difficult for us to even see if we have a wave or not. So the first step is that we need to pre-process these images into a state where we can start, first of all, see our gravity waves before we can do any analysis we want to do. So after the original image, the next thing we did was that we removed the stars, because the stars sometimes affect the parameters of high frequency waves. So we remove the stars here. And then as we can see, we don't have any stars here, but we do have the city light, the effect of the city light, part of the Milky Way galaxy also there, which of course we cannot really do anything much at this point. And then I also say we can't cheat nature, but Ricardo always used to tell me you cannot cheat nature. Okay, so in this case, this is nature, and we are just trying to reduce the effect that nature is presenting here. Now, after this, we try to remove the curvature effects of the camera. Okay, so now we try to project the image onto a different plane, that is a horizontal plane where we can now see clearly. Of course, in this image, you cannot see any wave activity, but in this, we can see that we have this dark curve-like structure here, followed by the bright one and another dark one. So these are wave activity. So it is in this stage that we will say that we are now going to analyze the image in order to take our wave parameters before we go to the next stage of the work. Now, to determine the parameters of this image, what we do was that we selected some regions where we can clearly see these dark and bright bands in the image. Then we create a time series image, as you can see here. You can see some rectangular regions selected here. These are the regions where we want to perform the analysis to extract the wave parameters. So what we did was that we pick one of these regions, then we create the time series for the images, then we pick the interesting points, that's the crest of the wave, and then the trough of the wave. We create this time series, then we can see the oscillation. Then seeing that oscillation, now we apply discrete Fourier transform in 2 dimensions. Then after that, we obtain the amplitude of this oscillation and then the phase. Then after that, we determine the horizontal wavelength, the observed phase speed of the wave, the period, and then the propagation direction. However, we can also use a power spectrum, okay, but we have a problem with the power spectrum. Why? Because it can give us the wave parameters except the propagation direction, because there's an ambiguity in the estimation. So we normally use the power spectrum to just confirm the estimation of the parameters, but not to determine the wave propagation direction. So this is how we determine the parameters of the wave. Then now that we observe the wave, we pre-process the images, and then we extracted our wave parameters. The next thing we did was to now run the retracing model in order to know where the wave was generated. Our interest here is just to know the source of the wave. We are not interested in where it will dissipate. Okay, so for the retracing, this is how it works. We have 3 stages of the retracing. The first stage is we feed in the wave parameters that we estimated using the spectral analysis. Then we define some constants that is needed for the model. Now, on the other side, we take the background data set. Now, the background data set here is temperature and wind, because for gravity wave to propagate in the atmosphere, the temperature and the wind play a very important role in the propagation of the wave. So we need these parameters in order to see how the wave propagated. Then, for us to go to the next stage, we need to define an initial altitude step. Okay, now I said that the retracing helps us to study the propagation of the wave in the atmosphere. So now we are defining a 200 meters mark. So what we are doing here is every 200 meters, we want to see the behavior, the position, the time of the wave in the atmosphere until it gets to where the wave or the model will tell us that the wave was generated. So we define this time step, altitude step, then we follow each 200 meters down to the ground. So after we define this step, what happens is we go to the stage 2. In the stage 2, we estimate the gravity wave position and vector. Then after that, other parameters are estimated. Then after these estimations are done, it passes to a boundary condition. We have 4 boundary conditions here. And if all these boundary conditions are satisfied, the retracing now continues to determine the next time increment. So after the next time increment, we are able to estimate the next altitude step, that's the next 200 altitude step. Then the process continues. So far as all the boundary conditions are satisfied, this process continues until the point where one of the boundary conditions are disobeyed. In that case, what happens is that it moves to the third stage where all the calculations will be saved, and then we end the process. So after the process is ended, the model presents the results, that is the time, the altitude, the position, and a lot of parameters. So we pick them, and then we do a plot of this kind. This plot is just for the latitude and longitude variation in the Fourier part. Okay, so this is how the retracing basically works. Now, after we know where this wave was, or let's say is generated, we need to investigate about the source of this wave that I would say the retracing is trying to, I won't say it's absolute, but it's trying to suggest to us that, okay, the wave might be generated from this region. So now we want to now investigate the region that the retracing is pointing to, that the wave is generated there. Then we now do further analysis. So in this case, we want to know the height, the extension of the height by which this overshooting, okay, occurred. Is it more than 1 kilometer mark? If not, then we remove it. If yes, then we know that we have a point, then we can continue. So to determine the overshooting top height, that is the pushing upward, the height at which the cloud have been, or the tropopause have been pushed, we take data from radiation measurements, where we determine the tropopause parameters, that is, we determine the tropopause temperature, then the tropopause height. Also, we determine the K. The Kp here is just a convective available potential energy. So this is the energy that the air parcel within the cloud needs to have in order for the clouds to be formed. Okay, so if you have this energy, which gives us a proxy about formation of clouds, we can also use this particular parameter to estimate the velocity at which that warm air is moving. If it crosses a particular threshold, then we have a higher possibility of an overshooting occurring. So we need a cape also in this case. But then I think for this analysis, we don't need it here. It's just for compliments. So knowing the tropopause temperature and the tropopause height, we take another measurement from a ghost satellite, which takes the cloud top activity, the temperature on top of the cloud. And then we use the infrared images here, because as I said, the coldest temperature region is the overshooting. So we are using the infrared, where we determine the minimum cloud top brightness temperature, that's the CTBT. So this is where we are able to know that, okay, if we have the coldest region or the minimum cloud top brightness temperature, we have an overshooting. And we can also determine the overshooting lap rate, which in this analysis is not so much of a focus for us. So at this particular point, we know the tropopause temperature, and then we know the tropopause height, and we know the cloud top temperature. So we can now estimate the cloud top height. So with these three parameters, we are able to determine the cloud top, that is the overshooting top. Okay, the height of the overshooting top, we are able to determine it. Then after that, we do this estimation for several images. So we pick the coldest region in several images, and we find the maximum for each image. Then we've plotted it with time to see how it's going, because if we say our wave is generated plus or minus 20 minutes, that is the error margin, then we should be able to take about 50 minutes images. And among these 50 images, we determine the region which has the coldest cloud top, which signifies the highest overshooting. Then we plot it with time and see which of these images within the error margin has the highest overshooting. Then we can say it is possible the one with the highest overshooting height is the source of the wave. So that is what we did here. Then after that, we pick the positions of this particular highest overshooting tops. Then we overplot them on the map to also know the position in longitude and latitude where this overshooting occurred. So to do this, this is just the simple methodology. We pick the cloud top parameters from the GOES observation. Now we know the minimum cloud top brightness temperature. Then we know the overshooting height. Okay, so we know the height of this cloud top. So knowing the height, we correspond it to the position. So we find the position of this overshooting, that's the highest overshooting top. Then we plot it over the map. The reason why we are plotting it over the map is that we want to see if this particular overshooting, highest overshooting, corresponds to the center and also where the ray tracing is pointing to be the likely location of the source. If this, overshooting top would be well distributed within the point located by the ray tracing to be the source. If yes, then one of these might be the source of our wave. So this is the methodology that we employed in this work. Now, the result we had from San Martinho, as I explained earlier on, is quite different from the traditional one, or let's say the previous ones we had. So in 2019, October 2nd, to be specific, we observed two different concentric gravity waves. Sorry, here the image seems not to be so clear like the ones I showed, but within this dash dotted red region, we have these concentric structures here. But for this image, you could see clearly here that the bright and then the dark structures are not straight line, they are curved line. But the region here shows the first concentric structure that we saw on the image. Then for the second wave, we also saw something here, which is not so clear, but within this region, as you see the pointer, that is where we have our concentric structure. So having this, we knew that something definitely happened to generate this wave, because the overshooting, as we know, when it occurs, one of the manifestations is that we have concentric rings, if and only if the overshooting meets that round kind of, or have that kind of stone-like or point-like nature, as I showed earlier. So having observed this, we definitely know that something of that nature occurred, but this is science. We can't just jump to conclusions, so we have to investigate further. So what we did here was that I'll talk first about the wave one. What we did was that we traced the propagation of this wave, or let's say we studied the propagation of this wave in the atmosphere down to the lower atmosphere. And then we realized that, okay, we have the retracing, that is the blue line, which is the model wind, and then the dot dash red lines being the zero wind. We realized that all of them seems to be pointing to almost a region at the center of the circle we have here. And then within this center, we have a very cold cloud top structure here. And then the temperature scale of this cloud top structure is defined here. So we're looking at the temperature scale. We have the cold region to be about -80 to -85 degrees Celsius. So this temperature range already is pointing to us that this particular region has actually pushed up the tropopause into the stratosphere. So this is one indication. Then in the figure B here, this is the altitude versus time plot for us to see the variation in the ray path. And we realized that we could not see much variation. And this indicates that, okay, the wind during this time was not really strong. And this is evident in this plot, because we could see that both the zero wind path and then the model wind paths are all pointing to almost the same position. So this is one indication that the wind is not so strong during this wave. And then I would say, luckily on our side, we have it also pointing to the coldest region of the cloud top, which shows that this wave was most likely generated within this region. Okay, but then let me do a zoom in to show something. If you look now inside this cold region, we could see that we have another colder region inside the cold region here. So at this point, these regions that we are seeing here is normally the convective cores, convective overshooting cores, which is actually the one which is protruding into, or let's say protruding upward. So we have to now study in details and get some information about this. But the criteria we are using here is that this core here is different from this core here. So what we need to do from now onwards is we have to pick this core. Then in the next image, we look for this core again. Then we trace only this core until it disappears in this region. Then we come back and then pick this particular one. Then we trace it also in time and in space. Because at this point, this one is overshooting, and this is also overshooting. And then if we have other ones over here, they'll also be overshooting at the same time. So in this case, we will not be able to know, because this region is quite big, and then the whole of this region is not most likely to overshoot at once. So these small ones, we need to be very careful now to determine the exact one, which is the source of this wave. But then I'll talk more about the method later. Okay. So for this, we are convinced that the ray tracing is able to tell us where this wave might be generated. For this plot, let us not bother about it, because I have it zoomed out in the next slide. I'll talk about that one as time goes. Now, coming to the second wave, because I made mention we have two waves that night. So the second wave, this is the ray tracing result of the second wave. And now we also realize that the wind the model wind path also came all the way to this region, okay? All the way to this region where we have a very cold region on the cloud top, showing that we have some very rigorous convective overshooting going on. But then when I zoom out this one also, now we can see clearly what I was trying to explain, that we have other spots that are much colder than the cold region we are talking about. So here is it. You could see this one is colder though, but within this, we have this. So let's assume this is where, not assumption anyway, but let's take this position to be the source, okay, or the altitude at which the wave was generated, as shown by the wave path. So anything within this region could possibly generate the wave, overshoot to generate the wave. But interestingly, this region is between -80 to -85 degrees Celsius. Now you have another colder region, which is between -85 to 90. Then now over here, we have another darker region, which is -90, okay, less than -90. So here we can clearly see that we have this convective core here, which is overshooting. We have this one, which is likely overshooting. We have this likely overshooting in one image. So in this particular point, we need to determine individually their overshooting altitude for all the images we are going to consider within the error range, which is plus or minus 30 minutes in this case. So we are talking about 1 hour, 10-minute images. So we have to look for this particular overshooting core. We trace it in the image, this 1 hour, 10-minute images. And then we do it for this, we do it for this, we do it for this. Then after that, we now come and analyze it further to see which one has the higher probability to generate the wave that we are observing here. So this is where we are beginning to have a different approach to the one we used in the past. And as I told you, also looking at this plot, we also realize that in terms of the altitude and the time variation, we have some slight variation between the model wind, which is the blue profile, and then the red dash profile, which is the zero wind. There's difference. So this difference we can say has accounted for the difference between the wave path here, because for the red dash red wave path, it has ended here, but for the blue one continued to this region. So we could see that the wind played quite a very important role here. Now, I would like to show one very important thing here. For this system that we are calling the Mesoscale Convective System, is actually a characteristic of deep convection, where you have the convection occupying a very large area, okay, which is the characteristics of this one. And compared to the one I showed earlier, you realize that they are just centered within a particular region. But this one, actually, based on literature, it has the characteristics of a Mesoscale Convective System. And as you can see, this system is moving about 11 kilometers every 10 minutes. So this is another reason why we cannot use our traditional method of just focusing at one position, because the cases are presented in the literature. Actually, they are just at one position, even though they are evolving with time. What I meant by evolving is that they are changing their position. You have some regions overshooting, then they fall back, but the entire system wasn't moving compared to this. So now we could see that the entire system here is moving towards the southeastern part. So in this particular case, it makes it now very difficult for us to just decide to say that, okay, when we see any cold regions here, we just pick one of them and say, okay, this is where the wave was most likely generated. But we cannot do it, because the image I have at this particular time, which is 1050 UT, the next image, which is 21 UT, okay? I'm sorry, I think think it's not 10:50. Let me just go back. It should be 20, sorry. 20, that is 8 o'clock local time. Okay. 8 o'clock. Okay, 8 o'clock, not local time, just 8 o'clock. So now, at the point where we have something like 23, which is 11 o'clock, this is the system that we have. Let's say at 23:50, the system have actually changed its position. So this is where we got stuck a little bit to think further before. Hopefully we came out collaborating with one of the researchers in INPE who is an expert in this, and then she told us this is totally a different situation, that we need to apply a different method to investigate the source. And that is what we did here. So what we did here is that, as I showed you small patches of very cold regions. So what we did was we pick all these small patches, and then for each image, each 10-minute image, we determine the coldest region. Then we do that for as many patches as we can see. Then after that, we selected the ones that are most likely to be the source. And in this case, for the wave number 1, we have those patches, as I'm talking about, are actually the convective core. We have 4 convective cores, which are the ones pushing out the tropopause to overshoot and then possibly generate the waves we are observing. So we have 4 prominent ones for wave number 1, and then for wave number 2, we also have 4 prominent ones. And then we did this analysis in time with respect to the images. So for wave number 1 and wave number 2, this is the time range. We have from 2 o'clock UT on the second to about 4:10. And then for the wave number 1 is around 29:40 or 29, yeah, 21:40, sorry, or that is 9 o'clock 40 to midnight. And we trace this points or these convective cores, or let me say patches. Okay, we trace them back in time and forward in time because of the plus or minus 30-minute error range we use. So we did that, and then this is what we found. That okay, now for the first wave and then for the first convective core, we started tracing the first patch or the convective core from around 9:40 thereabouts, all the way to around 23 o'clock UT. And then this is the profile that we've seen. And then we realized that averagely, this core overshot more than 1 kilometer. That is the first thing. Now, when we come in terms of space and time, the distribution of this core is seen here, as we can see. Let me just do a zoom so that it will be very clear. Okay. Sorry. Okay. So you can see now the movement of this core here in space distributed around this place. And this one is actually within the center, and then the precision where the ray tracing showed that the wave might be generated. That is the first. Now, when we come to the second core, which is this one, the orange one, we started our analysis from around 21:40, and then it also ended somewhere around 23:15 or 23:10 thereabout. And then we could see that averagely the system, or sorry, this core also overshot more than 1 kilometer. Now, following it in space, we realized that, okay, it also has its distribution around this region, which is quite closer to the position determined by the ray tracing and then the center. Now we go to the third one and we traced it, and averagely the third one didn't overshoot more than 1 kilometer. So this is already, should I say, eliminated, because we don't have an average overshooting of 1 kilometer. So we are already eliminating it at this point. But then let's see in terms of space what happened. In terms of space, we could see that it's quite far from the center. So To us, there's no way this system could possibly generate this particular wave that we observe here. Now we go to the fourth system, and then here we also realize that averagely it overshot, let me say, plus or minus 1 kilometer. So it's within the range. And then we realize that no, this particular system in space actually is far from the center. So it is at this particular point that, based on this overshooting height and also the distribution in space, we eliminate some of these convective cores that could possibly overshoot to generate the wave. And then from here, we are eliminating the third core and then the fourth core. Why? Because one, their overshooting is not so strong, and then the distance of their position from the position of where the wave might be generated is far, so we can't. In this case, we realized that the wind during the propagation of this wave was actually weak. So we cannot also think of maybe the wave being generated here and the wind going to push it to a different location that much. Okay, so these ones have been eliminated. Now it's left with these two cores. And then among these two, we realize that this one, the orange profile, is a bit far away, even though close to the central point of the source location, but it's still a bit far. But then what actually drew our conclusion here is that whilst this convective core was also overshooting, this one was also overshooting. But when you compare their overshooting altitude, the convective core 1 have overshot higher than this convective core 2. So based on this criteria, we can say, or we can conclude at this point, that the convective core 1 was the one which overshot, most likely overshot to generate this wave, because the distribution of this overshooting also is close to the center of this concentric ring and also the retracing position, which is indicating the position where this wave might be generated. So for this, that is what we did in order to try our possible best to figure out which exact convective core possibly generated this wave, because one, it is the system is moving in time, so we cannot say is this one at this point. So we have to give room for other possibilities as well. And then by comparing them with their positions in space, we realize that this one is the most likely candidate for this wave to be generated. Now, we could see that we have some black, let me say, a contour plot beneath this plot. Actually, this contour plot is showing the wind at the tropopoles. I put this here in agreement to the team. We all agreed that we have to indicate that indeed the wind at the tropopoles was also moving towards the southeastern direction. So this is just to confirm. So the arrows here are just the vector of the wind, which is showing that indeed the wind was towards the southeastern direction, as the system is also moving towards the southeastern direction. So that is the contour plot and the arrows that we can see here. Now let's go to wave number 2. For the wave number 2, we did exactly the same approach I explained earlier. And then with that one, I'll go straight forward and then say that at this particular point, we are eliminating the convective core 1. Convective core 3. Why? Because the convective core 3 at this point is far away from where the wave might be generated. So that one is out. And also, it did not overshoot more than 1 kilometer averagely. So it is not a candidate. So that one is out. Now let's come to convective core 4. It is also out, though, but it has a very high overshooting around 3 to 310. Okay, the overshooting here is extremely high, so it is a candidate. But then we also realize that in as much as it is a candidate, when we come to convective core 1, it also overshot at the same time within the same altitude range. So if these two are all overshooting at the same time within the same altitude range, and this convective core 1 is closer to where the retracing is pointing to be the source, Then the convective code one is most likely the one which possibly generated this wave because of the distance between the position, and also the time of overshooting is the same with the same overshooting height. So if we analyze it just by thinking about it, if you have two systems overshooting at the same time and they're having the same overshooting height, and they have different position, and one position is closer to the source position, then for me, I will go for this one because it's clear that it's very close to the source position, whilst this one becomes the most unlikely one to generate the wave. Now, coming to the convective code 2 for this case, it is also closer to the point determined by the retracing to be the source of this wave. However, I'm looking at it here, where this particular system has not so strong overshooting. This one also have the highest overshooting at that point. So in this case, we can say that we have a continuous overshooting occurring within this time if we combine this together with this. So at this point, for me, I cannot decide conclusively that, okay, maybe the system 1 is the source or the system 2 is the source. What I can say at this point is they are all capable of generating. Why? Because this wave, we realized that the wind was a bit strong. So at this point, anything can happen. But what I can say in conclusion is convective core 1 and convective core 2 are most likely to be the source of this wave that we have observed. And this is what we have done so far with this, which took us some time to come out with this idea and also to carefully do it, because if care is not taken, you will be missing things up. So this is the new methodology that we came out recently to just analyze and determine the source. And I think this will be very good for those of us in the gravity wave field, especially to investigate the sources of gravity waves, to look at all these circumstances or situations before we further go ahead to investigate the sources of gravity, especially for a system that is moving. Okay, so for a moving system, we can't go the straightforward way, but we need to find a more, should I say, rigorous way to work it out. So in conclusion, I would like to say that this work presents two concentric gravity wave events generated by a mesoscale convective system. And then since this system is moving about 11 kilometers every 10 minutes, we have to develop a new methodology according to the work of Sansaba et al. 2009 in order to track, okay, the overshooting top in time and in space. So at this point, this is the tracking we did in time, and then this is the tracking we did in space. So now we have to use the tracking in time and the tracking in space to now decide which of these cores within this big system would possibly generate the concentric gravity we observed. So at this point, I would like to thank INPE because this is part of my doctorate work. So I would like to thank INPE for the opportunity. And then UFCG, since I have my professors still there that I'm working with, let me say UFCG, Physics Department in general, and then CMPQ and Campus for the financial support. And then the logos here actually, the data, where I got the data from, which is actually, I think, the source. Okay. So I would like to acknowledge them also for the data provided for me too. Thank you all very much for listening.
Thank you, Prosper, for your presentation. It was a very nice presentation. I think it's a hot topic. And now we open for questions from the audience. Please, if you want some question, you are free for asking to Dr. Prosper. of course, as I said previously, you can ask in português. Se vocês quiserem, pode perguntar em português também, escrever no chat. Prosper consegue entender.
Posso perguntar, Fábio?
Pode ficar à vontade.
Eu vou perguntar em português, tá?
Tá.
Eu acho que você vai entender. Olha, não é nenhuma pergunta, basicamente, é um comentário. Essa pesquisa sobre ondas de gravidade através de imaginadores aqui no Brasil, ela basicamente começou com a tese do professor Martinho, daqui do nosso departamento, tá? Lá no INPE. E o Martinho, naquela época, eu acho que em 2000, mais ou menos no início de 2000, deixou uma contribuição que essas ondas de gravidade que você descreveu no seu trabalho, ela tinha uma relação com fontes convectivas. Por exemplo, tempestades, tá? Do pessoal que é de fora da área aí, e sempre existia assim uma separação muito forte entre a troposfera, que é exatamente a região da atmosfera que a gente vive, que a gente respira esse ar, nós estamos na troposfera, com altas altitudes, tipo mesosfera, o topo da mesosfera, início da termosfera, que está em torno de 80, 90 quilômetros de altitude. Pois bem, existia, assim, sempre uma dúvida dessas observações de ondas de gravidade com relação a efeitos troposféricos. Mas tinha já uma forte relação. Eu não sei, Próspero, eu acho que o seu trabalho, ele basicamente, ele deu uma contribuição muito forte, porque você conseguiu, efetivamente, localizar a fonte dessas ondas de gravidade. Claro, para esse tipo de onda concêntrica. Tá? E qual é a grande vantagem das ondas de gravidade? Não é vantagem, tá? Mas qual é a importância das ondas de gravidade? As ondas de gravidade é como se fosse uma onda da onda do mar. E quando chega na areia, ela quebra. E eu acho que todos nós já tivemos a oportunidade de receber uma pancada de uma onda do mar no corpo e sentir que ela realmente é forte e derruba a gente. Então, essas ondas de gravidade, quando elas se propagam para cima, tá? Que normalmente é o que se observa, ela, ao chegar na alta atmosfera, ela pode quebrar. E nessa quebra, ela coloca muita energia, quer dizer, ela coloca energia, em momento, na circulação geral do vento. Então, se vocês olharem direitinho, é uma ligação direta entre o que a gente tem aqui embaixo e o que acontece também lá em cima. Então, pode acreditar, existe uma conexão entre essas camadas. Prosper, recentemente, Cosme, ele mandou para mim um vídeo de uma onda de gravidade observada no Havaí, que foi resultado do vulcão de Toba. Tá? Aquele vulcão que aconteceu, se não me engano, foi no dia 15 de janeiro deste ano. A minha pergunta é a seguinte: vocês continuam observando, pesquisando essas ondas de gravidade lá em Santa Maria e tiveram a curiosidade de ver uma propagação relacionada com o que aconteceu em Toba? Essa é a pergunta.
Okay, Prof.
Yes.
I get everything. So the question is if we have observed anything in relation to the Tonga explosion, right?
Yeah, the question is, have you ever observed gravity waves related to Toba? I don't know how to say in English, vulcão. Okay,
Vulcano.
Okay, vulcão in Toba. That's the question. Okay.
Okay, so far, I think since I started studying this type of wave, the Tonga explosion is the first I'm working on. Currently, we are working on it. But we realized that it could not propagate to Santa Maria, that's San Martinho da Serra. We couldn't capture it. Even though we have some other images we are trying to process now, we are not yet done, so I cannot say that we've observed it or not. But for now, until I finish the analysis before I can conclude whether it's reached there or not. But interestingly, I'm also working with some satellite data, which we observed this concentric ring right above the explosion, but not in Santa Maria yet. And there have been quite a number of papers that I would say they investigated much about the explosion, the past explosions. But so far, we have not yet observed anything like that.
Okay, that's all. Thank you.
Welcome.
Temos mais alguma pergunta? Se vocês quiserem, podem perguntar pelo chat também, tá? Escrever Oi? Alguém falou? Cosme? Foi você, Cosme?
E aí, Fábio, tudo bom? Boa tarde,
Tudo
pessoal.
bem, Cosme. Boa tarde.
Eu só queria fazer um comentário com relação à pergunta do professor Ricardo, é que o que a gente observou ainda, essas oscilações devido ao vulcão, ela chegou durante o dia. Então, não teria como a gente observar pelos imaginadores que só funcionam à noite. Então, essa é uma observação que... Eu não sei se Prosper comentou sobre isso.
Eu não entendi, Costa. Repete
É...
Então, aconteceu à noite, durante o dia.
As ondas chegaram aqui durante o dia. Foi isso, né, Cosmo?
Isso mesmo.
So actually, Dr. Cosme, I have some data set now that I'm working on. That's why I told Dr. Ricardo I can't categorically say we have not observed yet. So I want to first confirm. If nothing appeared, then that is when I can conclusively say that we don't have anything yet.
Okay, Prof. Thank you for the information.
Thank you very much.
Ok. Mais alguma pergunta da audiência? Eu tenho uma pergunta. I have a question. In fact, a couple of questions. Prosper, qual é a escala horizontal desses sistemas convectivos que geram as ondas de gravidade concêntrica?
Okay. So far, the scale I have from literature and then the ones I analyze for the system is between 15 to 25 kilometers. That's the horizontal scale of the overshooting region.
Tá. Uma outra dúvida que segue essa mesma pergunta, né? Você calcula o comprimento de onda horizontal dessas ondas concêntricas vistas nas imagens de Airglow?
Sim.
Você consegue estabelecer uma relação entre o comprimento de onda horizontal que você vê nas imagens de Airglow e a dimensão do sistema convectivo que está gerando essas ondas?
Sim. We did it in the first work, the paper we published. We related it because Sharon Vadas did that relation, so we also based on her methodology. So in the cases that we have so far, the relationship has been established. That is the period that we have, and then also the horizontal scale of the convective system, and then also the horizontal wavelength. So there's a relationship which she established, and then in our first paper, we also did the same relationship.
Ok. Eu tenho mais uma pergunta, né? Na verdade é uma dúvida, curiosidade, né? Como o Ricardo falou, esse estudo de ondas de gravidade no Brasil, ele começou há uns 20 e poucos anos, né? E a Mauri foi pioneiro e no início dos anos 2000, ele voltou do INPE e instalou um imagiador em São João do Cariri, né? E desde então, vários trabalhos, né, várias dissertações de mestrado, várias teses de doutorado têm sido feitas usando os dados de São João do Cariri, né? E a gente não enxerga, né, ondas concêntricas. Eu, pelo menos, nunca, apesar de não trabalhar muito com imagens, eu nunca vi ondas concêntricas aqui na região Nordeste, né, vistas com o imaginador de Cariri. Bom, eu suspeito, né, que isso tem relação com os sistemas convectivos que atuam por aqui, né? Os sistemas convectivos que atuam aqui na região Nordeste são diferentes dos sistemas convectivos que vêm lá do Sul. Você poderia comentar alguma coisa nesse sentido? Quero dizer, né, existe algum tipo de sistema convectivo particular que é mais propício a gerar essas ondas de gravidade concêntricas? Não sei se eu falei muito, não sei se você conseguiu entender o que eu quero perguntar, né?
Yeah, I think for Caribbean, we have some cases which in my first seminar, I presented them. But interestingly, we found out that Caribbean, we have about, I analyzed about almost 20 years of data from Caribbean, and then I could only get 25 cases out of the 20 years data. So one reason why we couldn't get much concentric gravity wave cases in Caribbean is because of the convective system. That is the convective activity. But within some months, we realized that the ones we observe are skewed towards a particular month where we have a lot of convection. That is during the rainy season. That is where we observe those cases. And then there is one particular case where there's no convective system, but then that one, I would say, is a different topic that we are currently working on because it has a different source mechanism. So for Caribbean, what I would say compared to Santa Maria or San Martinho da Serra, the occurrence rate is extremely low, which some other literatures have already used satellite data to do the occurrence rate. And then it was observed that in the equatorial region, we don't have much cases because of the less occurrence of the deep convective activity compared to the high latitude. So that is one thing I have to say. And then about the last question, I think I'm a bit lost there. If you can please repeat for me.
I think, na verdade, a minha pergunta você respondeu. Eu tentei, no fim, fazer uma síntese do que eu estava querendo perguntar. Mas você respondeu. Obrigado. Mais alguma questão da audiência?
Como que eu tenho a boca?
Fábio, eu tenho uma.
Cosme. É Cosme? Cosme.
Sim, sou eu. Prosper. If you change the window model, what is the result of the ray tracing? Is it change the localization of the source, or it's still the same? For example, if you use the HWM14 and Meta 2, what is the difference between them?
Okay, let me go back to this this result here. Let's see. Okay, for this result, for instance, this one here, I ran for both zero wind And then this one is the MERA2 and HWM. And then when I run for the HWM alone, it's ending around 58, minus 58 longitude, degrees longitude. So from this and then from this result here, I realized that depending on the structure, you could get as much as about more than 100 kilometers difference when you change the wind model. So there's a significant change because for this case, for instance, when I ran with the HWM, it didn't even cross into this region. It ended somewhere here. So there's a very great difference between the wind model. Unless, of course, for this case, for instance, when I ran for the 3 winds, they are all pointing to almost the same place because the wind was generally low. So further investigations, I got to realize that the wind, when it is low, both models are quite consistent, but at a particular time, it varies.
Thank you very much, Prosper. And Fábio e Ricardo, eu acho que esse é um ponto muito importante. Eu acho que ter dados de vento para explicar a dinâmica dessas ondas, não só as concêntricas, mas todas as ondas de gravidade. E São João do Cariri tem uma grande importância, né? Pelo radar meteórico e também pelo Fabry-Perot, de medir vento tanto na mesosfera quanto na termosfera. E eu acho que isso tem que ser ampliado para outras regiões do Brasil também, porque o vento muda de uma região para outra. E vento é muito importante na nossa área para tentar explicar como é a dinâmica das ondas de gravidade em particular.
Obrigado, Cosmo, pela contribuição. Muito boas as suas observações. Bom, se não tivermos mais questões da audiência, acredito que nós podemos encerrar por aqui. Eu gostaria de, mais uma vez, agradecer a presença de todos e, principalmente, agradecer também, novamente, ao Prosper por ter apresentado, mais uma vez, um seminário aqui para o nosso departamento. Obrigado, Prosper. Acredito que nós teremos uma outra oportunidade de você fazer uma nova apresentação e apresentar mais resultados recentes das suas atividades de pesquisa.
Thank you very much for the opportunity once again.
Ok. Até mais. Até terça-feira que vem. Né? Para o pessoal da audiência, terça-feira de vem teremos seminário novamente. Tá? A gente encerra por aqui. Um abraço para todo mundo. Boa noite. Boa tarde, boa noite. Cosmo está nos Estados Unidos, é boa tarde ainda. Ou dia, talvez. Nem lembro onde é que ele está mais. Até mais. Tchau.
Tchau.
A gente encerra por aqui. Tchau.